Let's continue to look at our common emitter amplifier, also known as the Class A amplifier. The last time we looked at the amplifier stage and talked about the DC operation. We understood that the voltage at the base is set by this voltage divider here. The ratio of the resistors would determine how much of the power supply shows up at the base. We also understood that the emitter resistor provides negative feedback so that if there's any drift in the beta or the HFE factor, it would be compensated for. The voltage in the emitter would rise or fall and contract or expand the voltage at the base to emitter junction. Now we're going to look at the input stage. And when we do that, we're going to enter the world of AC operation. In order to understand what's happening here, we have to review the role of our capacitors. Big capacitors will act like a wire. In most cases, the larger your capacitor, the more negligible the effect it has on your circuit. So it will pass everything onto the resistor, whether it's low or high voltage, and it's really not doing much to constrict the operation. They do make great smoothing capacitors, though, when they're in parallel. We'll talk about that more later. The smaller capacitor, on the other hand, will tend to choke the voltages that are slower. The lower frequencies will experience more of a impedance at the capacitor, and therefore the capacitor will take more voltage. It will take more work to pass through that current. So a small capacitor in series with a resistor will tend to choke the voltage at that resistor at lower frequencies, of course. You would be able to get it to act like a wire again by increasing the frequency. So now let's look at our input stage. We have a function generator that's set to 1 kilohertz, and the voltage, the input voltage is 1 millivolt. And you have a 5,000 ohm resistor in this loop. However, don't be deceived by that. It's actually interacting, this input stage is interacting with the entire voltage divider. Imagine that my DC power supply is grounded. We're going to do a superposition analysis here. We're going to ground the other sources and look at the effect of one source, which is our AC source. It's going to see these two resistors in parallel because the voltage from this AC source is going to split upward and downward. So it is the parallel combination of these two resistors that is seen in this loop. Since 25,000 ohms, if it was at full strength, if we had turned the potentiometer up to 100%, 25,000 ohms is much greater than 5,000 ohms. The parallel resistance would be set basically by the 5,000 ohms. However, at 34%, we're looking at something like 8,500 ohms, and that is pretty close to the 5,000, close enough to make a difference. So we're looking at a net resistance somewhere around 4,000. It's not very important to me that we look at the exact numbers here. We just need to know that there's an impact for the top resistor as well. Now, if we're looking at this as an RC circuit, we know that there's going to be a sharing of voltage, and the voltage divider is the input to the amplifier. So our goal is to get as much of the input into the amplifier as possible. So we would want to increase this capacitor so that there's less impedance, right? There's less impedance here, and more of the voltage is passed on to the voltage divider resistor. So let's see what would happen. The other thing that we can do is increase our frequency. that has the same effect of reducing the impedance of the capacitor. So let's do both things. Let's start by increasing the capacitor. Let's see what happens when I take it. Let's do an extreme example. Let's take it to 1 farad. Very big change. Okay. Now, notice this is the output that I had before. Let's run it again. Oh, wow. Look at this. I get a large change. The blue traces my output. So we see the effect is true. We're going to have a large increase in our input. I'm going to show you the scope of this. I have to increase my scale to 200 millivolts per division to capture the top and bottom. And notice something else that happened though. We have a 180-degree phase shift here. Let's remember what it was before. Here is where we were before at the 10 nanofarad. Notice that we're looking at something like a 90-degree phase shift. When the blue output peaks, my input is at the starting point or the 0 point. It's actually 90 degrees plus 180 degrees, which we'll talk about later. But you can see the 90-degree delay. So creating a greater separation between the capacitor's impedance and the resistor's impedance will do two things. It will definitely pass more voltage to the resistor, which is the input to the transmitter amplifier, and it will reduce the phase shift. It will shift it further so that it looks more like the pure 180-degree phase shift of my transistor amplifier by itself. So we'll just review that point right now. The transistor by itself, without any impact from the capacitors, will put a 180-degree phase shift on its input, simply because of KVL and Ohm's law. Your increase in current will reduce your voltage at the transistor's collector. So now we've decided that we're going to maximize the voltage at this resistor here. 10 nanofarads gave us this ugly phase shift, which is not what we want. So we could increase this to 10 microfarads and see if that gives us something that we would like. Let's see if we can find that. Okay, that result looks much better. All right. So the question is, why wouldn't we increase it to the largest possible capacitor we can get? Well, remember that there's two purposes to this capacitor. It is not just transferring the AC voltage to the resistor here, but it's also blocking DC, the DC signal coming from the power supply into the function generator. So we want to isolate the DC signal from the VCC to the function generator. And so a smaller value here will do that job better. Now let's move into the circuit towards the amplifier and the output. We could have decided to increase the resistance here because all we needed to do was create a greater separation between the two impedances. And so that meant we could have increased the resistor value also. However, remember that this is a voltage divider, and that means that we're assuming no current is flowing into this transistor's base, or that's the ideal assumption, but we will say virtually, practically no current is going into the base. All we're saying is that the current that is flowing is supposed to be very small compared to the current that's flowing through the voltage divider. Remember our basic circuits lessons, when we had a voltage divider that was loaded, that load would always bring down the voltage slightly because it was going to create a different mix of resistance. The load would be in parallel with the bleeder resistor, which is this 5,000 ohms here, and it would create an equivalent resistance that's less. That changes the ratio of the voltage divider. So the larger your load, the less effect you felt when you added it. So now we want to be careful not to raise this resistor too high. If it starts to get close to the resistance, the effective resistance of this stage that it's connected to, that it's feeding, you're going to impact the voltage division. You're going to create unwanted change, unwanted dampening of your base current. All right, so this is all about trade-offs. Now we'll move into this part of the circuit. We're getting close to the output, but let's look at this capacitor here. The emitter's capacitor is acting like a smoothing capacitor. Remember the power supply we studied earlier, where the capacitor connected to the output would allow the ripples to be smoothed out. And the input stage also had a smoothing capacitor that allowed any fluctuations in the input to be smoothed out. The capacitor would basically discharge if the voltage dropped, and it would keep the voltage that's it's feeding on the right side of the circuit, or for the load, it would keep that voltage constant. Now, of course, it depended on the time constant, RC, that's determined just how long you could keep that discharge flowing before you reached a lower level that was noticeable in the circuit. So the larger your capacitor, the better the smoothing out effect, the longer that time constant. So we have some intuition that says we want a really big capacitor here. And so I've put 400 microfarads. In parallel with the RE, it's going to allow the small ripples that you're feeling from the input to not impact the voltage at the emitter resistor. So VE, which is the voltage at the emitter, is going to stay pretty constant thanks to our capacitor here. Likewise, all of that ripple is going to be felt at the capacitor. And this is going to act like a wire for the AC voltage, just for the ripple. Now, it's going to maintain a VE base voltage, and it's going to fluctuate above and below the VE average voltage at the capacitor. Now let's see what happens when we increase or decrease this value. Okay, let's look at our beautiful signal here. Remember what this looks like, because we're going to make some changes. So right here, I've replaced the 400 microfarad capacitor at the emitter with a 1 nanofarad. It goes against our intuition, but we want to check it out anyway and see what happens. And look, my amplifier output, which was the blue trace, is practically gone. Let's actually decrease our scale and see what it is. Wow, we have really dampen that output signal. Is it still giving me any amplification at all? It looks like unity right now. Not even giving me any amplification at all. What I've done is increased the impedance of the capacitor by reducing it. So the AC signal is finding a larger resistance here. It's not a short anymore. And so the RE resistor is actually looking practically smaller. If you were to think of it as two impedances, two mysterious impedances in parallel, there's more current now that's going to flow through RE because C2 is a larger impedance. So we have reduced our effective gain. We have removed some of the stability at the emitter resistor as far as the AC isolation. It's going to see some of that AC current. And it's not working as well as we would have liked. So let's go back to the larger capacitor. Let's see what happens when we increase it. So now I've increased my capacitor to 4 farads. And don't ask me why I chose 4 farads. It just felt wrong to go above 4 for some reason. I just wanted to have a high number. Even 1 farad would have been sufficiently high to show the difference. And what we see here is that it hasn't affected anything except for the gain. It's still looking very strong, very high. And if I did go down to 1 farad, would it make an impact on the gain? Is there a linear relationship between this capacitor value and the gain? Let's see. Okay, so I look like I have just repeated the same signal. I'm not seeing much of a change after 1 farad. So the larger capacitor is acting more and more like a wire. And it's going to become an excellent smoothing capacitor, okay, that will allow the voltage across the emitter resistor to be constant. Okay, so you see the voltage here at 6.596 volts, okay, about 6.6 volts. That voltage will not fluctuate much across the emitter because of the capacitor smoothing effect. So now we see that the capacitor here is essential to increasing our gain because it basically takes the emitter resistor out of the circuit for the AC fluctuation. Okay. Now let's understand the third capacitor that's connected to our load. Right now it's connected to an infinite load, which is the oscilloscope. So this would be the no load operation. We've been looking at the output form all along. We're going to study the impact of this capacitor. Let's think about what we would expect. So bigger capacitor acts more like a wire, passes along all kinds of frequencies, low and high. Smaller capacitor will choke the voltage at the load. Okay, and it will store the voltage of lower frequencies longer. Well, 10 microfarads is what we have here. Let's check it out. Let's see what happens when we go very low. Let's do 1 nanofarad. 1 nanofarad. We have to stop the simulation and go. Oh, look at that. So we expected it to choke. And well, we're seeing that we haven't gone low enough to really choke it yet. And it could be because our resistance is so large, right? Let's just go a little more extreme. You have to realize that when you're pushing the limits of things, you have to think of other things that might be also at the limit, like our infinite resistance. So it could hide the effect of certain other components. Let's see if it's hiding the effect of this capacitor. Okay, so as you can see, I could take this capacitor down as low as I want, and it's not going to change much because I have no load attached. Okay. And we can go the other way as well. Let's see what happens when we increase it. Let's do 1 farad. Now, in this case, maybe we could see something different. Let's see. Once again, we don't have any effect. We have no load. The infinite resistance is not allowing us to see any impact of this capacitor. Well, it's time to start thinking about adding a load. I have a 50 kilo ohm potentiometer here. Let's set things up. So I've connected a 1 kilo ohm resistance at the load. If you notice, this potentiometer is set to 2% and its max is 50K. So 1%, 10% of that would be 5K, and 2%, 1/5 of that, okay, would be 1K. Now, the 1K resistance happens to be equal to the 1K resistor at the collector. So let's just keep that in mind. What we're looking at is a 10 microfarad capacitor here. And wow, I have changed my gain. I have reduced this peak, okay, where it was before at about 300 and change, it is now at 180 and change. Now, is this due to the capacitor or the load? Let's take a look at the capacitor. Let's change that first. Let's go low, nanofarads. Okay. And what do we see? Interesting. Now what have I done? I totally wiped out the output. There is no more gain here. And the reason is that this has such a large impedance now compared to the load that it's choking the load's voltage. So we see the capacitor does make a difference. How about if we go high? Let's go really high now, back to 1 farad. Huge capacitor there. Okay, and restart. We're back at the first gain we saw when we added the load, about 180 millivolts. There we go. Interesting. So with the load, we do have a limit at the bottom of how low we can go with the capacitor, because at some point we'll be choking the voltage at the load. But we don't really have a limit, or we don't see the importance of putting a limit at the top end of the capacitor. Okay, so right now we're just going to leave it as a large value, 1 farad, and see what we might affect later on at that value. But now we're going to have to think about this load, because there are other things going on here. At the 1 farad value, with no load, we had twice as much gain. What has happened now? Let's think about the physics, how this circuit is working. We're going to see the DC current flowing through here. This is ICQ, and it's going to set a voltage at the emitter resistor and the collector resistor. This input here that's passed through to the voltage divider stage right there is going to increase and decrease my base current. As the base current rises, the collector current also rises, and the voltages around the collector and the emitter will increase. But is the emitter's voltage really increasing? Yes and no. The voltage at the emitter, the resistance of 1 kiloohm, is not going to change very much. However, the current, the increased current, will flow through the 1 farad capacitor, C2. Now that is going to allow the voltage of the collector to rise because more current is flowing. But it's not going to allow the emitter to feel that increased voltage. It's all being shorted out to the second capacitor here. And when that voltage falls, because the current here falls, IB, this is going to discharge into the emitter, which keeps the emitter constant still. So we see RE should stay pretty flat at 6.596 volts. The capacitor, however, is going to be a sink and a source of the alternating current. It's going to sink the alternating current that rises, and when that alternating current falls, it's going to become the source to keep the current constant at the emitter resistor. Fine. So now we see the resistor at the collector is where the up and down motion is for the voltage. The transistor's voltage, which is part of our output here, is extremely important to our load. That transistor's voltage is basically the inverse, the opposite of the collector's voltage. Let's look at some of our formulas. The lowest that the collector voltage can go is going to be the emitter's voltage plus this special saturation voltage of 0.2. So that's going to be the floor for our collector. Then VC top, the top value, the maximum you can get, is going to be the situation where there is no current. So the base current is so low that it chokes all the current in the transistor. There's no current flowing here. And you're going to see that all of the voltage will be at the transistor, the collector and emitter voltage. So remember that VE is staying constant because this capacitor is providing the current when there is no more current coming from the transistor. So the voltage that the transistor increases by is the voltage at the collector.